Let's now study what are the different laws of thermodynamics, starting with the Zeroth Law of Thermodynamics. Now, the Zeroth Law is based on the concept of thermal equilibrium. Now, what's thermal equilibrium? Now, if there are two different bodies which are in contact with each other, let's assume they started off at different temperatures. One was hotter than the other, and then you bring them in contact. Now, after bringing them in contact, the heat energy from one will be transferred to the other, from the hotter body to the colder body. After a period of time, whatever that may be, these two bodies will have the same amount of energy, right? The temperature of both the systems will become equal. So that is called thermal equilibrium. Like when two bodies at different temperatures, when they are in contact at different temperatures, when they come in contact with each other, the temperature of both these bodies converge. Like the hotter one cools down and the colder one heats up, and they converge at a point, and then they stay that way. Okay, so that point is called thermal equilibrium. So the Zeroth law is based on the concept of thermal equilibrium, which says that like if there is a body, if there are three bodies A, B, and C, and A and B are not in contact with each other, there is an insulator, as you can see here, in between A and B, which is prohibiting the heat exchange between A and B. But there is free flow of heat exchange between A and C and B. So what if A and C are in thermal equilibrium and C and B are in thermal equilibrium? If these two hold, we can absolutely say that A and B are in thermal equilibrium, right? It's a very simple concept, didn't occur to come in as a law of thermodynamics, but it came later because of important implications that it had after we already had the first law of thermodynamics. And that is why, like, we already had the first law, but this one is more basic even than the first law of thermodynamics. So that's why we came up with this name of Zeroth law, right? Like just even more fundamental than the first law of thermodynamics, and that's why the name Zeroth law, right? So this is a very simple concept, but it has applications like when you are taking the temperature using a regular thermometer, in which you have to keep the thermometer in physical contact with your body. So what happens in that situation is that you give a little time for the thermometer and your body to come in thermal equilibrium with each other. So how do you measure the temperature of your body? You are using Zeroth law of thermodynamics. How? Because when you're reading the thermometer, you are not reading the temperature of your body. You are reading the temperature of the mercury inside the thermometer. But since Zeroth law of thermodynamics holds, since you gave enough time for your body and the thermometer to come in thermal equilibrium with each other, both these will have the same temperature. So that's how, like, the Zeroth law of thermodynamics is that fundamental, right? It's very intuitive, very, very common. Okay. Now, Zeroth law is very fundamental. Now, moving on to the first law of thermodynamics. Now, in my understanding, first law of thermodynamics is also very, very basic. Why? Because it's energy conservation. It's just energy conservation put in terms of work and heat. Now, we have learned energy conservation in our high school, in preliminary classes, in which we have said that energy cannot be created nor it can be destroyed, right? So what happens is energy from one state changes from one type of energy to a different type of energy. Like in the case of a battery, so you have chemical energy stored in the battery. Now what you can do is you cannot create or destroy. You have chemical energy in the battery. Now you can use that chemical energy to transform it into lighting a bulb, so light energy, or a heater, heat energy, right? Driving a fan, kinetic energy, things like that. So you can change from one form of energy to another, but you cannot create or destroy energy. So it is as simple as that, the first law of thermodynamics. It just applies that fundamental concept to heat and work. Now, we have some decent idea about heat, like we have some intuitive idea about heat. We also have some intuitive idea about work, but we often miss the relationship between heat and work. They have similar units, right? Like heat is in form of energy. It has energy it can be expressed in joules, right? Calories. Same goes for work. Okay, work is also expressed in joules, like the energy of work is joule. So there might be some kind of relationship between these two, right? Now, this relationship is more evident and more clear when we study it ahead. But like when we apply energy conservation to heat and work, this is the fundamental first law of thermodynamics. That's what it does. Okay. So let's understand what heat is. Okay. Now, heat is a form of energy. So let's assume you have a body which is hot. Say you have this duster in which assume that this body is hot. Now, what will happen why do you feel that this body is hot? Because heat from the body is coming to you, because this body, this system, this duster is giving you heat. So heat from this duster is getting into your body. So when heat is flowing from the body to you, shown by this green arrow, from the body to the surrounding, the body being this duster, surrounding being you, the heat is coming out and you feel hot, right? Because of this heat coming to your body, inside your body. So that's what we call an exothermic process, right? Heat from the system is coming to you, you are feeling heated up in here, right? So exothermic, exo means out, the heat is coming out of the body, and we represent it as a negative sign. Why? Because it's losing heat, right? So we just say, okay, it's losing heat, the heat is coming from the body to the outside, and that's why you are feeling the heat, and that's why it has a negative sign. Opposite can be a colder body. Say you have ice in here. Now, if you have ice, heat from your body will be flowing inside the system. So from the surrounding being you, to the body being this ice block. Now, heat is going in the ice block from your body, you feel cold, right? And this is called endothermic. Why? Because it's going in, heat is going in the system. So it's called an endothermic, the heat transfer is endothermic, right? And we represent it as the plus because the system is gaining heat. Very simple concept, exothermic and endothermic. Exothermic, the body is losing heat, and that's why negative. Endothermic, the body is gaining heat, and that's why the positive sign. Okay. Moving on to the energy concept. Now, work, if you have a piston like this, we already we have learned in basic physics that work is F dx, like force times displacement, right? Like, and the displacement, so if the force is being applied by these gas molecules which is trapped inside this piston, this is applying a pressure on this piston, right? Now, force divided by area gives you pressure. So if you want to find out force, you multiply it with the pressure. So you have pressure times this area will give you the force that is applied by these gas molecules on the piston. So once you do that, you have the force. Now it's applying the force from this direction, from left to right. Now this piston, because of this force, can move forward, right? So this xi can become xf, the xf being more than xi. In that case, the gas inside expands, right? The force applied was this way, and the delta x with the dx being xf minus xi is a positive number because it has gone out, right? Say this was 10 centimeters in here, and this has now become 15 centimeters. So the dx is 15 minus 10, which is 5, which is a positive number. So force is in this direction, dx is positive, you have an expansion, and therefore the work done here is positive, right? Now, the opposite is, when we see the opposite in here, we see here that the force is applied in this way by the gas molecules, but because of some external factor, because of some external force, this piston has come inside, has reduced in xf. So in here, just the opposite thing happens, and dx becomes negative. So f dot dx becomes a negative number. Now, when f dot dx becomes negative, work becomes negative, and this is compression. So during compression, work is negative. During expansion, work is positive. Now, what happens in thermodynamics is sometimes we get confused. Is the way physicists look at things and way the chemists look at things are slightly bit different. But let me assure you, there's no difference between the first law of thermodynamics. Science is there to understand how nature works. So nature won't differentiate between how it works just because you're a chemist or just because you're a physicist. It's the way you see things. It's just the way different sciences, different branches of science apply different conventions. And that's why there's a slight difference between the first law of thermodynamics in physics and chemistry, which we'll see how that differentiates. But let me assure you, there's no difference between the first law in physics and the first law of thermodynamics in chemistry. Right? It's absolutely the same, the one and the same. Okay? So in here, I hope that you understand that during compression, the work, the sign of work is negative, and the sign of work is positive in expansion. Why? Because force and dx is the same direction, so that's positive, and the opposite is happening in here, and that's why we have a work negative in compression. Now, the first law is absolutely simple. Why? Because you see, we have the same piston in here. What I have done here is given an external heat from in here. Okay. Now, you are giving heat to this system. Simple, right? This burner is providing this piston an amount of heat which is denoted by Q. Say. Now, you are giving it heat. Now, this system, the gas molecules, what they get is the heat. They are getting heat from the outside. Now, what they want to do is they can use this heat in two ways. They can increase their internal energy. They can speed up the molecules can speed up their velocities inside. That can increase their internal energy. Or what they can do is push this piston up, doing some work. Now, when these gas molecules push the piston, they are doing work, right? Now, this can be used in two ways, therefore, like to increase the internal energy or to do work. This is the first law of thermodynamics. If you give heat, that heat will be used either in two ways, to increase the internal energy or to do work, right? It's as simple as I give you $100 and you can use that $100 to either save it in your bank account or go to and make a trip to somewhere, right? So I gave you $100. Now you can spend $20 doing some going somewhere, like traveling, and the rest $80 will be saved with you as your savings account. This is first law of thermodynamics, right? So what I said is heat given will be either used in increasing the internal energy or doing work. So if we heat will be represented as Q, right? dQ. Energy is E and work is W. Okay. So now if we have heat, a small amount of heat del Q, a small amount of energy dE, and a small amount of work del W, this will be the same, right? The heat is either going as internal energy or it's doing some work using that, right? And when it is expansion, it is positive. When it is compression, it's negative. Okay. Now, why do we have, so this D means a small change. Now, why do we have different signs? We have different signs because energy in here, the internal energy, is a state function. To represent that it is a state function, we have used a different symbol from here, the D. And since Q and W, the heat and the work, are path functions, we'll see what that means. I have used like different symbols in here just to represent that. Now, this equation, the heat is equal to internal energy plus work, is simply written in mathematical form in here. So just rearrange. If we get the W on the left hand side and rearrange here, what we see is D internal energy is equal to the heat given to the system minus the dW of work. Now, if the external heat provided was 10 joules and you used those 10 joules, 2 joules were used by this gas to do some work. So what is the amount of internal energy left? 10 minus 2, 8. It's as simple as that. It's like I give you $100 and you use those $100, you use $20 to do some traveling. What remains in your account balance is $80. It's as simple as that, right? You can use that $80 entirely to save it or spend it or do whatever combination of things possible, right? So this is as simple as that. So the first law of thermodynamics is just this. In slide, in a different video, we'll see why the sign changes in the physics and chemistry are a little bit different, because the chemists try to look at things a little different way. But let me assure you, the first law of thermodynamics is just this. If you understand this correctly, thermodynamics first law is not going to change.